Talk about equilibrium laws. An equilibrium law is an algebraic expression, so we're going to use a little bit of algebra. Expression based on the balanced equilibrium reaction. So that's a key there. You have to use the balanced equilibrium reaction, right? In other words, you can't use, well, we'll see here, but basically we're talking about equilibrium. That's this whole chapter. We need to make sure we are talking about equilibrium. This didn't turn out very well, but you guys have a copy of it, so I'm not too concerned here. In a general equilibrium system, you have, for example, little a and big A here. Little a refers to the coefficient out in front, so maybe a 2 or a 3 to balance that chemical equation. So this is your coefficient here, as is little b, little c, little d kind of thing. Those are your coefficients, you know, to balance this chemical equation. A, of course, is the substance that you're trying to balance. So H2, N2, NH3, HCl, things like that. All right. The equilibrium law would be the following. So the equilibrium law could be written like this. Kc is the constant we will call this. So C, of course, refers to the constant. K is the equilibrium constant. So the equilibrium constant is denoted by Kc. It is going to be a number, and we'll talk about what that number means later on today. You're going to take, of course, C. So that substance, maybe it's NH3, for example, and the coefficient is going to be to the power of. So that is going to be the coefficient there. Little c, little d is the coefficient. We're going to make those powers. All right? And, of course, this substance D here to the coefficient power. All right? You'll notice what this is the products, this is important, over the reactants, always. And it's always that. It's the products over the reactants. Okay? Not Hess's law. That's different. That we did that already. This is products over the reactants. You're going to be multiplying this stuff together. Don't forget, when you go to divide these numbers, you need to use perhaps big brackets here to make sure you're dividing by the entire number on the bottom. Don't forget that. All right? So, how do we write equilibrium law? Equilibrium laws, basically using this Kc thing here. So let's take a look. Well, it says here, gases are included in the equilibrium law. So gases are always good to include. So we can include all these things here, and it would look a little something like this here. We'd say Kc is, by the way, what does the square brackets mean again? What do the square brackets mean? Concentration, sure. So we're going to be still talking about concentration here. We got SO3, gas here. Products, that is my product. The 2, of course, was the coefficient to balance that 2SO3. And we have SO2 here. Once again, a 2. And some O2 gas here, like so. That would be my equilibrium law for this particular equilibrium balanced chemical equation based on this right here. Okay, so 2 is the coefficient. We're going to raise that to a power in O2. Products over the reactants. Okay, so that could be an equilibrium law to represent this. All right, good. Questions, anyone? Products over reactants. And yes, the square brackets means concentration, so we'll be doing something with that shortly here. Dissolved solutes, so aqueous solutions are included in equilibrium laws. So if we take a look at this one here, our equilibrium law would look something like this here. Kc is equal to NH4 plus aqueous, CH3 COO minus aqueous, all over NH3 aqueous, and what is it? COOH aqueous, like so. Okay? So aqueuses are included in these, like I said, in these equilibrium laws. All right? We don't need to write the ones down. If you notice, this was balanced. Of course, it was a 1-1-1-1 relationship or ratio. We're not going to put ones down for the powers in this case. But obviously, don't forget we are raising it to a power there. A, B, C, D kind of thing. All right. Next. Good so far? Straightforward. Now, solids are not included in equilibrium laws. So we don't ever include solids in an equilibrium law. And this is something, obviously, that you're going to have to remember here. So Kc is equal to, okay? Well, the product in this case here is a solid. We're not going to include that. So we're going to leave that blank for right now. And we're going to go to Au3 plus, aqueous. And I got F minus here, aqueous. Don't forget there's a coefficient out front of 3. And on the top part, I'm just going to put a 1 to hold that place there, basically, just to, like I said, just to basically hold that place. We don't include solids, so I got to put something up there on the top part, so I'm just going to put a 1 up there. All right? So solids are not included in equilibrium laws. You want to go sit there? Okay. All right? Good? Liquids are also not included in equilibrium laws. So things like, for example, when you see H2O, right? Water. Water is a liquid. We're not going to include that in the equilibrium law either. So in this case here, Kc, of course, is, let's see, what did we have here? I forget the H3O plus, aqueous, and Cn minus, aqueous, all over, what was it, HCN? Yeah. All over HCN, aqueous. And I don't think we need any coefficients with that, no. So water is a liquid, we're not going to include that in this case here. And remember, it's always the products over the reactants. All right? So that's what we would use for that one there. Solids, liquids are not included. Aqueous gases, yes. All right? Yeah. Yeah, sure. Alrighty. So we're going to write equilibrium laws for these, of course, here. Once again, we're not going to include solids or liquids. So pretty straightforward, I think. Just you have to keep in mind that that's the case. Please don't forget after a while when we start doing some other stuff. All right, Fe2 plus, we will include, that is aqueous. Square brackets implies concentration. So Ag plus, aqueous, concentration, and Fe3 plus, aqueous. And we will leave out, of course, the Ag solid. So that would be the first one there. B, in this case here, we have Kc is equal to the oxygen gas, and that is all, because the other two are solids. And finally in C here, we have the Kc value, which is 1 over the HCl aqueous and the TiOH aqueous. All right, and that's what we would have for those ones there. Okay? So hopefully that's all good for you there. Now, we're going to use this basically to build on this, and this is kind of, you know, last day we talked a little bit about equilibrium and how to calculate those concentrations at equilibrium. Well, now we're going to plug it into what you just finished learning here today, and we're going to calculate the equilibrium constant based on those numbers. So we're going to calculate a value for Kc, and we'll talk about what Kc means for you later down the road here at the end, so you're just going to have to be a little patient here. Equilibrium concentration, and once again, this is really important, it's the equilibrium concentration, okay, of each reactant or product can be substituted into the equilibrium law. Equilibrium concentration, equilibrium law. We need to make sure we're using those numbers to solve for Kc. So here's your first example. I think you guys could probably have enough information. If you're following along, you should know how to do this, so go. Okay, here we go. So once again, you're starting with your ice table. 0.066, 0.017, that's a decrease of 0.049, right? If that one's decreasing by 0.049, that means I have to use twice as much, 1 to 2, so twice as much. This has to decrease by 0.098, which of course means I make 0.098 here. I know that's really incredibly hard to see, but that's what's going down. Yeah. Well, I subtracted 0.066 from 0.017. Subtract those two. Okay? Then you're going to simply add or subtract, and your final numbers here will be 0.045 moles per liter, of course. And over here, you will get 0.166 moles per liter. And I'm going to get off that now because that's pretty tough to see. Is that okay? Can you guys see that okay? I know it's not the best, but I'm going to not do that anymore. But 0.045, 0.166, yeah. I didn't subtract 0.058, I subtracted 0.098. Yeah. Okay. Now, Kc values tell me, or equilibrium law tells me the following. I need to take NO2, the concentration of that, squared over NO squared and O2, just like that. Okay? You're going to substitute the numbers in, of course. So Kc tells me at equilibrium, I should get 0.166 moles per liter squared over and NO is 0.045 squared and 0.017. Well, I put the concentration in, but the top part means concentration, yes? So it's a little different. I'm multiplying numbers, I'm writing concentration. All right? Final answer here, when you calculate this, will be 800. Okay? So, all right? Now listen, once again, okay guys, quiet. Once again, you have to understand that you got to use correct order of operation. You have to type this in the calculator properly. If you don't, yes, you will not get 800. I don't know what you'll get. You'll get something different. So don't forget, there is basically, if you're going to do this all in one step, you need to make sure that bottom part is an actual answer, right? You're taking the top divided by the entire bottom part. So you will get 800-ish point something, whatever, doesn't matter. And ultimately, guys, you know, as far as significant digits go, you can still use those. Okay, but I'm going to tell you right now, most of the time with these questions, we're probably not going to be calculating Kc as far as, well, I shouldn't say that, but if it is a numerical response, it's going to tell you you want 3 or 4 numbers, and if it's a multiple choice, obviously it's going to be there for you. I wouldn't worry too much about significant digits with this. Most of the time with this, I like to have just a number, like you know, 800, or if it was 39.5, usually we keep about 3 for these. I'm going to tell you right now, 39.5 is good, you know, 0.00457 or something like that. So you could write it as, you know, scientific notation as well. It's not a big deal, okay? We'll talk about what this number means in a little bit here, okay? All right? So here's the next one. Let's calculate this here. Now this one here is a little bit different. This one already says calculate N2O4 at equilibrium. So this is already at equilibrium. I didn't give you the initial one. You don't have to figure out the change. This is at equilibrium. So this is even quicker and easier. The difference is we want to find this concentration given that the Kc value in this particular one is 375. So once again, why don't you guys go ahead and figure out how you're going to manipulate this for that. All right, go ahead and solve for that one. Oh, you're wrong. All right, that's okay. We'll fix it right now. NO2O4 gas, okay? N2O4 gas, Kc, right? How are we going to solve for N2O4? Well, once again, if you want, just put the numbers in and solve for N2O4 like you would. That's fine. If, having said that though, you know, can you just put the numbers in, solve? Sure. Should you be able to rewrite this expression for N2O4? And the answer is yes, you probably should. That could be a, well, I would consider a gimme kind of question on your test. So how would I figure out the concentration of N2O4 in this case? I would take NO2 gas squared over the Kc value, yes? In other words, solving for N2O4. Cross multiply, solve, however you wish to do it. I don't care. Like I said, I think I told you this last year in Chem 20. At this point, I'm not going to fix how you do solving for N2O4 in this particular formula. You do what you got to do. If you want to multiply both sides by N2O4 and then divide both sides by Kc, or I don't care. But this is what you need to come up with here. Okay? So N2O4 concentration is equal to NO2, which is what? 0.934 moles per liter squared over 375. And all said and done, you'll get 0.002326 moles per liter. That does have a unit. You are solving for the concentration, not Kc. Listen, Kc doesn't have any units to go with it. Kc is kind of like pH. It's just a number to represent something, which we'll talk about coming up here. There's no units that go with Kc numbers. There is with concentration, so it is 0.002326 moles per liter. If you want to use significant digits, I'd say, well, probably 3 and 3 probably is a good bet here. I'd probably round it to that there. Let's see, 1, 2, 3 times 10 to the negative 3 moles per liter would be an acceptable answer for that one there. Okay, good. Or you could actually write 0.00233, I guess, kind of thing. Okay. Yep. Yeah. Oh, okay. That'll make a difference. All right. Next. I gave you another one here, and you might say, geez, Bachek, I'm getting kind of tired of these. Like, stop it already. Well, too bad, because I'm teaching you, so you're going to do what I tell you to do. This one's just a wee bit different, and I did this one on purpose, of course. So go ahead and try this one here, and you'll see what we're talking about once you get to that. It's not, I mean, it's not ridiculously hard or anything like that, but it just threw a little thing in. Okay, so here we go. So once again, in this case here, we're going to solve for NO2 concentration. All right, well, let's start with the Kc value. Once again, this is already at equilibrium, so I can simply use these numbers. If it's not at equilibrium, you got work to do, okay? You have to do the ice table. All right, so Kc here works out to be NO2 gas squared over N2O4 gas concentration. Let's see here. We need to find NO2, so to find NO2, it's up to you how you wish to do that. Let's stop talking, please, because you're being rude right now. So you're looking at that all said and done here, okay? That's basically kind of how you need to solve for NO2, nitrogen dioxide gas. And how am I going to get NO2? I got NO2 squared here. What do you need to do? You need to take the square root. Sure. So we need to use the square root in this case here. We're going to take the square root of the following here, which is, of course, Kc and N2O4 gas. Okay? So here we go. NO2 is square root of Kc, which is, in this case, a pretty small number, 2.68 times 10 to the negative 5. There's no units associated with that, so I'm not going to put any moles per liter in there. And 0.214 moles per liter. Okay? Okay. All said and done here, you're going to get square root of 5.73 times 10 to the negative 6. And when you take the square root of that, of course, you will get 0.002398. Or, once again, if you want to use some significant digits kind of thing, probably 3. I think that's what you have in this question here. 1, 2, 3. Something like that there. And, of course, this one, yes, would be in moles per liter because we are talking about N2 gas here concentration. So a pretty small concentration. Okay? Yes? Good? Okay. So that's what we should end up with. All right? Nice. What is these numbers, what do these Kc numbers mean exactly? Now I know in the last couple we figured out concentration stuff, but what do these Kc values mean here? Well, we'll talk a little bit about that right now, just to kind of end off here today. So this is, we used to do a little bit more with this as far as percent of the reaction that's actually taken place, things like that, but we don't do that anymore because it's changed since then. But the value of Kc is determined by the ratio of the products to the reactants. We know that. Kc is the equilibrium law, says the products versus the reactants. Three things can actually happen here, okay? Some equilibrium systems will favor the reactants, okay? At equilibrium, the reactants are much larger than the products. So Kc will be relatively small in this case. If you think about Kc, it's products over the reactants. If the reactants are very large, and that's on the bottom here, and that top part, the products, is a very small number, for example, 10 compared to, let's say, 1,000, you're going to get a Kc value less than 1, always, okay? And if that ratio is true, where you have a small number over a larger number, your number is going to be less than 0, or less than 1, I should say, sorry, less than 1. If your number is less than 1, it says that it's going to favor the reactants, okay? So we'll talk about that in a second. I'll come back to that. Vice versa. If the products happen to be very large, if the products are very large and the reactants are quite small, you're going to get a large number over a small number. Kc is, of course, going to be bigger than 1, which means it favors the products, all right? And finally, if some equilibriums favor neither the reactants nor the products, in this case you would have to say that the reactants and the products are probably approximately equal to each other. So very close to or around 1, right? Now usually you say, well, what's the cutoff there? Well, if it's around 1, guys, it's it's going to be both the same. If it's like 10 or 15 or 20 or 200 or 300 or 800, like our example, it's going to favor the products. And if they're really, really small, like in one of our examples, 2.35 times 10 to the negative 5, well, then it's probably going to favor the reactants. What does that mean exactly? Well, basically what it means is if you take your reactants versus products here, okay, this is an equilibrium. So as far as percentages wise and things like that, I will talk about it a little bit, but we're not going to get too involved in this. Look, you can't, it's got to be, the reaction of this has to be more than 0. Because basically, remember, if we have to use, we can't just have, you can't consume all the reactants in an equilibrium, right? You can't use all this stuff up, because this stuff is going to make the products, of course. And you can't just have nothing but reactants, because the reactants are going to make the products. And if you just had products, they're going to make the reactants, and they're going to go back and forth. So the percentage of this has to be somewhere between 0, right, and 100. And it's never going to be 0, it's never going to be 100, okay? Because you're not going to just have products, you're not just going to have no reactants, right? You're not going to have those two extremes. It's going to be somewhere in between there. Who knows? Okay? What Kc tells you is this, okay? Is that if you had a Kc of approximately 1, let's start with that one, what I would say is that about 50% of the reactants give you about 50% of the products. So about 50% of these would react to give you this product here. Roughly. Now we're not doing percentages, we're not doing that, but I'm just trying to explain this to you. So about 50% of the reactants have reacted to give you the products, okay? If the Kc value was greater than 1, the products are favored, right? So what that means is that probably more than 50% of the reactants have reacted. It could be 60, it could be 70, it could be 80% of these have reacted to form products. It could be 90 or 95 or even 98% of the reactants have reacted to give you the products. All right? So it's a number to kind of basically tell you how much stuff has reacted. And if the Kc value was less than 1, right, we know that the reactants are favored. So probably most of the reactants stay as they are. You know, for example, if we had H2 and N2 to give me NH3, most of that would probably stay as H2 and N2. All right? And we would say that maybe, you know, only 5%, maybe perhaps, you know, 95% here. These are extremes here probably, but maybe only 5% of the reactants have reacted to give me some products. All right? 95% of them probably stay independent, stay as reactants. All right? That's what the Kc value tells you, basically where you are in this progression here. Where is what's happening as far as how many reactants are actually taking place. And as far as a certain number, I can't tell you that because we're not going to talk about that. We're not calculating that. Maybe it's 10, maybe it's 15, maybe it's 20, maybe it's even 45 for that matter. Don't know. Okay? Doesn't matter. But that's kind of what the Kc value tells you, how much of the reactants are actually taking place, reacting to give you the products. All right? That's what that value tells you. Okay, so let's take a look at this one here. Calculate the Kc. Now that you've done one, you should be able to do this one, combining everything together that we've learned so far, and describe the equilibrium position for this system. So go ahead and do that. Doesn't matter. Last one's all we remember you by. Perfect. Okay, so increase, starting at 0, equilibrium concentration is that, so that's an increase of 0.86. Quiet, guys. So once again, if I'm making 0.86 there, I have to use 2 to 1. I have to use 0.43 here, and once again, 0.43 here. So adding those up, of course, I'm going to get what? 0.01 here, and this one was 0.17 moles per liter here, moles per liter, of course, and moles per liter. Those are the equilibrium concentrations, which I have to use in my equilibrium law. So therefore, we're going to write that out now. So Kc is equal to HCl gas. Be careful that these are things that you can write in the equilibrium. So we might give you all this stuff here, and we might give you a question that says something about solid or liquid in that question. And when you come to equilibrium law time, you can't use that value there. Okay, so don't get tricked by that. So, and then here we'll put in H2 gas, of course, and Cl2 gas. All right, so Kc value, depending on that there, is what? We got 0.86 here squared over, let's see here, 0.17 and 0.01. And once again, be careful calculating that there, calculating all that out using brackets, etc., etc. You get about 435, and of course this will favor the product. Okay? Favors the product. All right? So that's kind of combining all the stuff that we've talked about so far. I mean, there's a little bit of theory stuff there that you absolutely have to know, absolutely. But that kind of takes care of all the kind of stuff we've done over lesson 1 and all the stuff we did today as well. Now, a couple things that you will have to know as far as theory stuff goes as well. Kc, the magnitude of Kc is temperature dependent. So Kc will switch its number based on temperature. Okay, we'll get to that eventually. And the magnitude of Kc cannot be used to describe how quickly equilibrium is reached. What that means is, if one equilibrium system is, let's say, has a Kc value of 200, and another one has a Kc value of 800, that doesn't mean the Kc value of 800 is any better than the one at 200. That's not what it's there for. Okay, you can't compare those systems or anything like that. Different products, different reactants, all that stuff. It's really solely for each one of those. Okay, it's kind of an independent number based on that particular system. So we can't make those judgments. Okay, so we're not going to use that for that. All right, good.